61A Lecture 38 Q&A. Actually, this is not a Q&A about Lecture 38. It happened before Lecture 38. There were no Lecture 38 videos, only the live Zoom. But people did ask questions about the course, mostly about exams, but a little bit of conceptual stuff. And we had an interesting conversation about the relationship between computing and finance.
Sure. So what's a stream? Because that shows up on past exams. And what's the point? We didn't cover it, you're right. A stream is a linked list where the rest of the list is computed lazily only when someone asks for it. So much like an iterator, where maybe the rest of the iterator, the next element, isn't computed until someone calls next on that iterator to get the value. A stream is a linked list with the first element that's explicit, like represented in memory, and rest, which is a function or a procedure if you're in scheme. And so when you call rest, then you run this procedure and you compute the rest of the stream. But the rest of the stream might be just computing the first element and then another procedure which would compute the rest of the rest. So it's a way of representing really long, unwieldy linked lists without running out of memory by representing them in terms of procedures. It's a lot like an iterator, except for it's kind of like Scheme's answer to the iterator, because iterators are mutable. Every time you call next on it, you get some new thing, whereas a stream is just a first and a rest, but the rest might not be computed yet. And if you want to know more, you can go find the old streams lectures from back in the day. Let's see if we can find one. So here's a web address for previous versions of the course. Here we're in fall 2019. Did we do streams back then? Yeah, we did. So there's a whole video series on it if you want all the details.
I like that, John, back in the day is 2019.
Wow, a lot has changed since then.
When I was a youngster.
The next question was about the relationship between computing and finance. Does it make sense to predict markets using computing techniques? And why is that so hard?
Yeah, I can answer the first question. So I've had a few students over the years who've gone into this business, right? FinTech and doing predictive modeling. It's a big part of Wall Street. A lot of my former friends from grad school also did the same thing. I would not say that they've all failed, by the way. Many of them many of the models do very well. Consistently doing well is very hard. My understanding of the space, which in fairness is not that deep, is that the most successful are these things that do these micro tradings, things that happen at the like almost nanosecond. So for example, my favorite example of this is I had a former student working in this where they moved their headquarters like 2 blocks down the street because it was closer. The internet speed was like faster by like 10 to the minus 1 over 10 to the minus 9 seconds. Yeah. So these really rapid tradings can find slight weaknesses in the system. To your question about, why is it so hard to predict the market? Well, in some ways, there's a very easy aspect of the market to predict, which it goes up. Like we know historically, go back as long as we've had historical data for the stock market, it goes up roughly 7% every year. That's the returns on the stock market. Ups and downs, lots of variation. That number, by the way, is closer to 5 to 6% now, just post 2008. So there is, if you go look at the trend, the stock market does very well. Now, having said that, if you're looking to trade over decades, you can do really well. Stock market will go up. If you're looking to trade on months, days, weeks, it is irrational. Now, there are some pretty good models, and you only have to do better than 50% of the time. Right? You don't actually have to have 90% accuracy. So most of the really good models are like 51%. It's sort of like, think about the Las Vegas casinos. What are the odds of the casino winning? It's like 50 point something, right? It's just slightly better than chance, but long term, that's the ball game. Yeah. So to your question, it is a chaotic system. There's a huge number of variables, but there has been success in making predictions, and lots of people make a lot of money doing this in the market.
Okay, so two different people, you get two wildly different answers.
Excellent.
Here's my take. Um, there was a time when there was just tremendous amounts of money to be made in simply predicting what was going to happen in the stock market through variables that were available, readily available to anyone in the finance industry. And this happened really in like the late 90s onward. The people who are most successful at this were the people who invented statistical machine translation, the thing that underlies Google Translate. They didn't work on Google Translate. They worked on it before that in the late 80s and early 90s. And then they sat around, and they were like, what else could we use this predictive technology for? Because it was basically predicting sequences of words. And they thought, well, it probably would work for speech recognition. And they made some progress there. And then they disappeared from academia because they realized, oh, this would probably work for the stock market as well. And they started a firm called Renaissance, which is like one of the huge hedge funds in the world. And they just made a killing. I mean, obscene amounts. One of the effects of people performing this kind of algorithmic trading is that they make it more difficult for everybody else. So there's this idea called the efficient market hypothesis, which is that if a market is really efficient, meaning the prices represent the value of the things you're buying, then you can't do any better than chance if you just buy and sell stuff without like doing any useful work. And it's very clear that the stock markets around the world are not efficient. There's lots of people who have found ways just by buying and selling based on existing information to make a lot of money. Every time someone does that, they tend to kind of take away the opportunity to do exactly the same thing from everybody else. They sort of make the prices more reflective of the available information in the world. And somewhere around, it's hard to pinpoint, but maybe 2014, 15, so many people were doing this that it became a whole lot harder to make money just from like running predictive algorithms because everybody else was doing that. And so basically like any signal that you were using to predict from, somebody else was already doing that. And if it was a positive signal, then the price was going up because they were doing it too, right? So now it seems like people make more money by finding new sources of information. So like if you take satellite imagery of the parking lots of stores, you can figure out what their sales are going to be like because you can see how many people are going to the stores, things like that.
Or Google trending words was another popular thing recently where people were looking at Google Trends to see if they could predict the market from which words were trending.
Right. Yeah. And in the early days of Google, there was a lot of soul searching about whether they should just play the stock market from what they knew
Right.
from their search logs. And they
Right.
decided not to. But they probably, you wonder, is it the case that companies ever decide not to do something, even if it would be profitable? I think that's an example of where they decided not to become a hedge fund. They decided to continue becoming a search engine.
Yeah.
So, they still made fabulous amounts of money. So I guess it didn't matter in the end. Yeah, I don't think now is a great time to like do something even moderately complicated and expect to have stronger returns than just like putting money in an index fund and waiting for it to go up. There are definitely groups that are still doing this, but they have to go to great lengths in order to like get an advantage now.
John is absolutely right. This has gotten much, much harder because so many people have gotten in the game and people are trying to eke out these really tiny edges to sort of do better. But it has gotten much, much harder. But I'll tell you, I've had students, back in the day, and I think John is right. Things started tipping around 2015, about 5 years ago. It was like they were printing money. It was insane. Now, you could question the ethics of all of this. Like, what are these people actually doing? Like, they're not actually doing anything that's of real value, right? They're just finding slight inefficiencies in the market. That's an interesting conversation to have over a cocktail. But John's right. It has gotten much, much harder to do this.
Next, we did an exam question, summer 2019 final exam, question 7B. We also looked at 7A. I've cut that part out of the recording. 7A is out of scope for this semester. It's about how to build a stream, and we didn't cover streams this semester. If you want to learn about those, you'd have to go look back at the videos from fall 2019. There's a whole lecture on that. But you'll see it on past exams. You don't need to know anything about streams. Okay, so on to 7b, which was about scheme and was in scope. One of the things that this part of the video skips over, which was in the definition above 7a, was that there's this thing called a sequential procedure, defined just for this question, which is a procedure that takes a non-negative integer argument, 0, 1, 2, 3, 4, and gives you the element of the sequence at that index. So element index number 1 would be f called on 1. So it's just a way of representing a sequence as a procedure.
How would you write a procedure that if you represented a sequence as a function, that's basically what f is. So f called on 0 is the 0th element, and f called on 1 is the first element, and that's how you get the elements. How would you find the first duplicate? I think one way to find the first duplicate is to keep track of everything you've seen so far in an actual list as opposed to in a function. And when you see a new element, you figure out whether it's something you've seen before by using this contains procedure. So what does contains do? Well, it takes a regular old list, S, and a value. If S is empty, then the value isn't in there. If V is equal to the car of the value, then the value is in there. Otherwise, you have to check the rest of S. Okay, so we could do this where I think the key here is that duplicate takes an F, but in order to make progress, you need to track more than just F. You need to track where you are, and you need to track what you've seen so far. So where we are at the beginning is 0. What we've seen so far is nothing. And so we need to define the formal parameters for this. It's going to take 2 arguments. We'll call the first one I, which is the position where we're in, and we'll call the second one seen, which is the stuff we've seen. If it's the case that what we've seen so far contains the element at index I. Now we have to look at everything we've read so far to figure out how to get the element at index I. Well, it's that F is a procedure where to get elements, you call it. So this says, have we seen the element at index I in this sequence, which is represented as a procedure? If so, then we found the duplicate. So it's time to return the duplicate. Otherwise, we haven't found the duplicate yet, so we have to keep searching. Let's move on and search for starting with position I plus 1. But now we've seen something that we haven't seen before. Now we've seen fi, the value, and we've also seen everything we've seen so far. So I think that's what this would look like. You asked about what does it mean to be properly tail recursive. That just means that when you call helper, there's no real work left to do after that, which is true here. So we're not recursively calling helper, we're just calling cons. That happens right away. This happens right away. So the only thing left to do when we call helper is compute its value and return it. There was a lecture about tail recursion. It was optional if you want to read about that. We're spring 2020, final 1b. We get a function called prime, which returns the smallest prime number larger than n. Okay, but it doesn't tell us how it does that. And then there's some crazy thing called again. Let's take a look at what it does. It assigns f and g to the prime functions. It defines an h, which when called on x, redefines g to be some horrendous thing, a function that takes h and then takes y and then calls h on f on y and then calls that on g. Okay, so we have that function. And that gets returned by again. Okay, complete this description. Calling again returns a function h that takes an x and the result returns the result of applying prime to x repeatedly how many times? Well, I guess we have a counting game. X comes in, so we're basically trying to describe this thing. What does it do? It takes the number x. I see. And it does, in fact, return a number. It's just doing it in kind of a funny way. It's doing it in the following way. H is the name of the function, but it's also rebound as a value, which is the result of calling g on x. But which g?
I'm going to pause here for a second to tell you that what I'm about to say in the video is completely wrong. I do eventually correct it like much later in the video, but I just wanted to warn you in advance. I said that when you call g of x at the end of a multiple assignment statement, it's going to be the new g that you just assigned, but that's not true. That's not how multiple assignment statements work. In multiple assignment statements, you evaluate everything on the right using the environment that you have, and then you make changes to it by rebinding the names on the left, all at the end after you know all the values. So now I'll play the video, but just be warned that it's wrong.
Well, in fact, it's a brand new g. So f is prime, that never changes, but g is this thing. And the question is, what happens when you call this thing on some x? What's interesting about this expression is that it contains g. And this expression contains g and will be evaluated in its entirety before g is reassigned. So just like labeling this a little bit, this g will just be prime. That one. This g will be the big lambda h whatever.
And the f is also going to be prime, yeah, John?
And the f is always prime. And this h is not this h. It's whatever this h is. And this y is this y. Okay? So when we call this big lambda expression on x, which is what got passed into h, that means this h here and this h here, this call expression is that as the operator and that as the first operand. So this g over here isn't lambda h, it's lambda y dot dot dot, this lambda y dot dot dot, because we've already called this lambda h on prime. Okay? So that means, why is this white? I don't want a white line, I want a dark line. Aha. Okay. H is prime. F is prime. All right, I'm not going to draw lines. H is prime, F is prime. We've now used this G in order to fill in H. So what we have is prime of Y. And that's what we call on X. All right, where's the number K? Again, returns a function H that takes the number X and returns the result of applying prime to x repeatedly. Oh, here's where k is. Oh, but every time you do this, you're changing g. So if you call h multiple times, then you've changed g from prime to prime of prime multiple times, except for this isn't always prime. This is prime the first time, prime the second time, and
this may be one of the worst exam questions I've ever seen in my life, John.
Prime the third time. Okay. So calling prime is not a big deal. There's no all h. I think that's nonsensical. Where k is the total number of times the prime is recalled. That's nonsensical. Okay, so this is
this is really bad. I like that it's like this nested multiple choice where you have to define the variable in addition to it. Good God Almighty.
All right, so k is the number of times that this h function has been called. And if we call it once, then we're going to prime twice. And if we call it a second time, then we're going to prime 3 times. So just like following that number, I think we got that.
So that's wrong. A student pointed that out right away. It's due to the problem that I was describing earlier. Eventually, I will correct it in the mutterings that follow.
Presumably, I wonder if there's multiple right answers depending on, like, is there a different answer if you define K differently?
Well, no, I don't think any of these really like scales up with the
Yeah.
number of times that it happens. So this is the thing that when you call H a bunch of times, then you're definitely changing what H
Right.
does each time. Um, when you call it the first time, what I got was that it primed twice, which is why I got K plus 1. I wonder why I got that it primed twice. It's because we passed in prime here, and F was already prime, and we called that on Y. X was Y, and so we primed twice. Yeah, we did.
Oh,
We did actually declare that these tell us the behavior of the function questions will not happen, and we did that based on feedback from a prior exam, which was this exam. So now we see why students didn't particularly like this question, and so don't spend too much time on it because you won't see anything quite like it. I'm still a little hazy on
Professor?
why it's K times instead of K plus 1 times, but if someone wants to explain that, that would be most welcome.
I'll spare you the period where I'm just staring at the problem.
I figured out why it's K times. Oh, it's K times. You know why? Because of the way assignment works. You first evaluate everything on the right-hand side before you ever change G and H. So this call won't be to the new G. This will be to the old G. You prime the first time. Lambda Y the second time. So if you're just calling prime the first time, that's one time for one time. And then the second time is when you're going to be calling prime prime. Gross.
Okay,
Okay,
yeah.
I agree with the answer key, though clearly I would have gotten it wrong on the exam. So there you go. By the way, I just had an idea, which is that I should really write next year's exam now and then wait until next year and see if I can still solve it. And if I can't, then I'm probably okay. Among Us, an environment diagram that is on the discussion 14 handout. Question 3.3 says, define a function which does something and then defines a function which does something and then assigns f to something that actually has a dot expression in it. That's probably a reasonable hint that G is going to be bound to a list and we're going to append or something. And then we do something else, and then we return F, and then we return U. And we're right, G is a list. But notice G started out as 1, 2, 3, and then the 2 and the 3 disappeared. So I'm just going to quickly draw them in there, and then we can disappear them when the time comes. All right, scaled equals the result of calling among, maybe I need to make this bigger, on G. So here's that call. Here's the local G bound to the same thing as the global G. There is a U and an N here. Well, here's the U, but I don't see an N. So it must be that the N is defined here. And what is N? N is 2. Can't tell you what this is yet. All right, we define this function and return it. Is that what the environment diagram says? Yes, exactly. It was returned as scaled, and then we see pink 5 is assigned to scaled of 1, which means we're calling the U function on 1. That looks pretty good. We're creating a new function that's a lambda, and that's here, so that's good. And then what happens to it? Well, we don't know, except for we do know that F gets called. And here's the call. So F gets called on 1, and that means S must be 1, which it is. Okay, we learned nothing new there. So we're kind of like finally the interesting part, which is like what happens in here. We're going to take in an argument. We're going to add the result of, I think this almost has to be pop. That's really the only thing that removes a value and lets you do something with it afterwards. And pop, recall, removes the last element of a list and returns it. So the first time we pop, we're going to get 3 plus whatever x is plus whatever n is. So now if we can figure out what x is and we can figure out what g.pop is, we'll know what n is at the moment. All right, and the return value of that lambda is 5. What was passed in is 1. We got the pop off is 3. Boom. 1 and 3 makes 4. How would we get to 5? It must be the case that n was 1.
This is wrong too. It turns out that n, which is part of the body of the lambda function, will not be evaluated until that function is called, which is after the blank line in the inner function. That part where you see f of s is where the function gets called. So we don't actually know what n starts as. We only know that n was 1 after one execution of that line. I got this wrong, and I'll have to go back and correct it at the end, which does happen eventually after some prodding from a student who was paying more attention than I was.
All right, if n was 1, but now n is 2, something must be changing n. The only way I can think of for that to happen is for n to be non-local and n to be changing. I don't know whether this is n equals 2 or n equals n plus 1. Let's try n equals 2, see what happens. Okay, so what have we accounted for so far? We've sorted all this stuff out, and we've even gotten this 5. Now we have to see what happens next. Skeld gets called on 2. There's the 2, which gets passed in here. And what we're doing is we're taking this 2, adding it to the result of popping this off, so that's 4, and adding that to the result of n, which is now 2, and so we get 6. So we've accounted for that as well.
Yeah, this is a little tricky. You notice that for part A, John couldn't tell right away what that was. You had to sort of get a little bit further down and then go back up. I think D is also a little ambiguous, right? That could be n equals n plus 1, it could be n equals 2, but it doesn't matter in this case.
Well, we did do it twice, and this didn't end up as 3. It ended up as 2.
Good. Right.
Actually fairly constrained, but it wasn't obvious to me that that was the case until after we kind of worked through it for a while.
Yeah.
So so it is a good idea to, after you fill in the blanks, retrace your steps, figure out what environment diagram you would get. You could do that by just dumping it into Tutor or by thinking through it. But that would help you catch things like whether this should be n equals 2 or n equals.
Hey, John, there's something in the chat that says n is modified before the lambda is called. So I think n has to start at 0 and then increment by 1.
Oh, brilliant.
Clever.
Okay, so why did this change happen? This would help to actually draw the environment diagram. This n is not read. The value of it is not found until f is called, which is down here. So if n starts out as 0, is set to 1, then we get the 5 that we wanted. We call it again. We don't get n right away. Instead, we set it to 2, and we call it, and then we get the 6 that we wanted.
That's a good note. Thank you.
So I'm 0 for 2 for the day.
You got the thing about the trading right though, John. 1 for 3. What is the hardest topic on the exam? I think it depends on who you are.
I'd say the 2 things that students tend to struggle on is finding the right decomposition for some tree recursion problem. So like counting up all the ways of doing something, which is never like a huge part of the exam, but it's always on the exam. So either practice that a lot so you're really comfortable with it, or just, forget about that question. Both are reasonable strategies. And then the other thing that does tend to trip people up quite a bit is knowing how the object system really works. So if you're a little fuzzy on class attributes versus instance attributes, learning that stuff is a good idea because we tend to test for it.
One more question. Any tips for time management during the exam? It's hard to say that there's one strategy for everybody. The strategy that I usually recommend is to at least read through the questions once quickly, just to see what you have coming ahead of you. I like time to think, so I often like to read questions and then sort of move on to something else. And then when I come back to them, I advise students not to like burn a half hour on one question. If you're not getting through it, move on, and then loop back to it if you can. But other people have different strategies for doing this. I don't know, John, do you have specific things that you recommend?
I think that's all good advice, but my number one in this online exam era is do not use the interpreter until you're checking your work. Because you can lose so much time with like trying to get some random test case to pass. And you've already gotten like so much partial credit that it doesn't even really matter that you have one tiny little bug. But if you don't, if you lose, an hour fiddling with the implementation of something, then you won't finish the exam. So it's much better to go through the exam, just like think about the answers by yourself without trying to transfer them into the interpreter or something like that. And then if you want to go back and check your work because you have extra time, then it's fine to run the test cases however you want. But don't make that your like standard way of approaching these problems.
Yeah, I think I'm looking at the chat now. I think the 10 minutes sounds about right to me if you're spending more than 10 minutes. I think John's advice is really good, is don't get bogged down with getting everything perfect. You'll get a lot of partial credit, and it's not worth burning the time to get everything lined up perfectly in the interpreter. I think that's really good advice. How do you get faster? I think the only way to do it is just keep doing problems. Now, there's an interesting twist here. There's a little bit of a danger of just doing problems, because you get into this mode of memorizing, which is not what you really want to do. Really, so I think the questions will go faster when you actually understand the underlying techniques, the underlying logic, as opposed to it's not biology, right? You can't just memorize your way out of this type of material. So be a little careful with doing problems, it shouldn't be about, well, here's the answer to this problem. It should be, here's the logic, here's the underlying principles that were critical to understanding this. Yeah. And then that's what will make things go faster, because there's just an infinite number of questions that can be made for you, and you're never going to be able to memorize your way out of this. John and I were talking about this. I think there's some folklore around this course, right? Some people think you can memorize your way out of this, but John, I'm curious if you think that that's true.
There are certainly patterns that emerge multiple times, but the most efficient way to get ready to solve all the problems is just to learn how to solve problems in general. The less efficient way is to have seen every problem before. And that doesn't always work reliably, because there's going to be some new stuff on every exam. I mean, all the questions are new. Some of them will look like old problems, but they'll never look exactly like the old problems. So if you don't understand the core of what's going on, then you're in real trouble. So if you're spending a lot of time practicing, fine, but make sure you're like learning what is new about the material. Like learn that pop takes the thing off the end, not the beginning, and learn that when you define a function, these expressions within it don't get evaluated until you call it. This kind of stuff is what's really going to get you through the exam. And then I would say about getting faster is that for most students, just don't. Like, if you really want an A+, then it might make sense to make sure you can go faster. But for basically all other goals, it's much more important to do the parts that you do right than it is to do all the parts.
Yeah. Last thing too, sleep before the exam. There's this illusion that if you just work your ass off up until the last minute, you'll do better. You will not. You will do much, much worse. You have to be rested. Your head has to be clear. I think it's a bad idea to study hours before the exam, because you get some weird thing wedged into your head and you're not thinking clearly. So, get 7-8 hours sleep, rest up. That's probably the single best thing you can do to prepare, is just be rested and,